So hello everyone, and welcome to our CHASPA course series on fundamentals of integrated sensing and communications. So this is the second lecture with the title Information Theory of ISAC, Rate Distortion Trade-off in ISAC. So our guest speaker today will be Professor Giuseppe Caire. So before we start, let me briefly introduce our distinguished guest speaker, Professor Caire. So Professor Giuseppe Caire is currently Alexander von Humboldt Professor with the Faculty of Electrical Engineering and Computer Science, TU Berlin, Germany. So he has received numerous awards, including the Jack Newbery Best System Paper Award from the HVE-BTS, the HVE ComSoc and ITSoc Joint Paper Award for 3 times, and the Alexander von Humboldt Professorship, and an ERC Advanced Grant, and also the 2021 Lebanese Prize. So he is a fellow of the HVE. He has served in the BOG of HVE Information Theory Society for many years. He was president of the HVE Information Theory Society in 2011. His main research interests are in the field of communication theory, information theory, channel and source coding, with particular focus on wireless communications. So without further ado, let's welcome Professor Giuseppe Caire. So Giuseppe, this is yours.
Yes, thank you very much, Pan, for the kind introduction. And I will hopefully manage to share my slides. Yes, I hope you can all see.
Yeah.
Good. Okay. So we can start. Well, first of all, thank you very much for inviting me to this very nice lecture series, very much needed on such a timely topic. It's a really good initiative. So after Fan's introductory lecture, the first lecture of this series, I think the audience know everything about the general ideas of ISAC and even more than that, but essentially it's a very fun area to work on because it allows us to look at the problems that have been traditionally separated, both in information theory and in communication theory and radar and imaging and remote sensing, and somehow bring things together. So today, the theme of this presentation is about the information theoretic aspect of ISAC. So a set of problems that have been studied recently by myself and many other co-authors and authors that have tried to look at the ISAC problem basically through the lens of information theory. And so we are going to look first at a model that I call monostatic. The key thing here is that the sensor knows the code word. So basically, a transmitter and a receiver wants to communicate. There is a sensor. The sensor knows what is being transmitted. Whether this is physically monostatic or logically monostatic is something that does not really concern us, because these models that we use in information theory are highly idealized. So all the practical issues of synchronizations and phase coherence and all these things are essentially bypassed, especially when we look at the discrete channel models. In this case, we will see a number of results, in particular the rate distortion region of this model. Then we will look at a particular form of distortion, which is called log loss, and which naturally introduced something that some people have called sensing mutual information or sensing. Good. Okay, so we were talking about here. So this monostatic model in particular, we will look at the linear Gaussian case that has been really studied in great details. It's also the closest to the application. Then look at what happened in the so-called quasi-static case, and when the sensor actually helps the transmitter, so when sensing can be seen as a form of feedback. And then we will consider another model that I call Bistatic, and this is the case where the sensor knows the code book but does not know the message. And we are going to see a few results, a few recent results on the Bistatic model. Good. So first, before starting, I would like to acknowledge all my co-authors. This is a partial list. I hope I haven't forgotten too many people. I apologize if I have forgotten somebody, but I really deeply appreciate the fact that there is such a good group of people and such a spirit of collaboration. So let's dive into the problem. So this is a model for the so-called monostatic sensing, where we have a transmitter and a receiver. The transmitter wants to convey an information message to the receiver through a communication channel. The communication channel may depend on a state, and the transmitter may have some form of state side information. The receiver may have a related form of side information, and there is also another device that we call sensors that observe another output of the same channel. This could be, for example, the backscatter channel or something. Anyway, some reflected wave that bounce around and convey information. And the goal of the sensor is to estimate the channel state. So it has to come up with an estimate of the channel state. So I call monostatic this model because we have this link here, which says that the sensor has full knowledge of what's being transmitted. So knowing the message and, of course, knowing the codebook means knowing X, knowing what has been transmitted. Good. So for this model, if we somehow delete the sensor and just focus on the communication only problem, well, this channel has been studied over and over, is the classical state-dependent channel with the channel state information at the transmitter and channel state information at the receiver. They may not be perfect, so the U and V may be jointly distributed with S, but not identical to S. And for this model, we know basically the capacity. In particular, for the general discrete memoryless channel, the capacity is always given by the maximization with respect to an auxiliary random variable t of this difference of mutual informations. The mutual information between t, u, y, and u minus the mutual information between t and v. And of course, we can distinguish the cases. So that the causal case, where the transmitter knows the sequence v in a causal manner. So at time I knows the sequence v up to time I. Then the maximum of this quantity is over the distribution of t, and a deterministic function x of tv, which maps the auxiliary variable and the channel state information, the current channel state information into an input. Oh, I have forgotten to say that this model is well known when the channel is memoryless. So we have the memoryless assumption. When things have memory, everything, of course, becomes much more complicated. And we will deal with a few cases, but not in full generality, because there is no general theory of channel with memory, unfortunately, at least no simple single letter theory of channel with memory. For the case where the channel state information is known non-causally, so at the beginning of the transmission, for some reason, the transmitter knows the whole sequence of channel state information at the transmitter from the beginning to the end of the block, then the optimization is on the distribution of in the conditional distribution of t given v and this deterministic function. So you will recognize that the causal CSIT was studied by Shannon first, in the special case where there is no channel state information at the receiver, and causal channel state information at the transmitter that is perfect. And then it was generalized to the case of the sort of extra channel state information by Salehi. Then for the causal case, the non-causal case, sorry, this is basically the famous Gelfand-Pinsker problem, which for the Gaussian case becomes the famous writing on dirty paper, that with some extra generalization with the presence of this additional channel state information. What is interesting is that under the condition that the channel state information at the transmitter is a deterministic function of the channel state information at the receiver, then the capacity for causal channel state information at the transmitter and non-causal are the same, and are given by this simple formula, which we all more or less recognize, because this is essentially a sort of, let's call it water filling over time. So this is how people have characterized eventually the capacity of the fading channels with channel state information at the transmitter and receiver. In other words, under this condition, we do not need the auxiliary random variable anymore. We can directly optimize over the conditional distribution of x given v for every given channel state information at the transmitter value v, and then do an average with respect to v outside. For the case of perfect channel state information, this has this familiar look, and for the fading case, this becomes essentially the famous water filling over time, which has been first proposed by Andrea Goldschmidt and then further investigated by myself and Shlomo Shammai, etc., etc. So these are all familiar results to some extent. And so now what happens when we also introduce the estimation, the sensing? So we can set up a problem where we have, quite classically, we have a message set of a certain size, a code book, so a collection of code words of block length n and rate r, a decoding function at the receiver that basically maps receive sequence and channel state information into a decoded message, and a state estimator that maps message and output for the sensor to some space of it may not be the same alphabet of the state, but something that we want to somehow, with respect to which we want to have like a state representation. And then we can define in a very classical way, the conditional probability of error given the message, which is a probability that the decoded message does not coincide with the transmitted one. The conditional distortion, which in general can be defined in this way. For these memoryless case, we normally consider distortion per letter, so we divide by 1 over n, so it's like a distortion rate if you want, and this L function is a general loss function or a distortion metric that evaluate the goodness of the output of the estimator with respect to the state, the state sequence. And then we have also a code word admissibility criterion. So we have a cost function, an input cost function, and per code word cost, and the condition is that this cost per code word is less than a certain quantity. So we can also relax these per message and per code word conditions and consider, for example, the case where we well, first of all, typical case is where the estimator decomposes into per component estimators, and the loss is additive, like, for example, mean square error, or square error that becomes a sum of terms over the component, or Hamming distance is another case. Then we can consider these quantities like average with respect to the messages. So we have an average error probability, an average distortion, and an average cost. And we can, whether with respect to this more strict parameters, strict conditions of per code word, or in this average sense, we can define a region that is all the tuple R, D, and B. So is rate, distortion, and input cost that are achievable, in the sense that we say that a tuple is achievable is for every epsilon there exists a code such that the rate is not smaller than R minus epsilon, the achieved distortion is not larger than D plus epsilon, and the input cost is not larger than B plus epsilon. And of course, the probability of error must be less than epsilon. So for this model, the rate distortion cost region is characterized by this theorem that was, in slightly different terms, was I think published in a paper by with Michel Wigger and Meraza and Mari Kobayashi, and basically he says that for a given cost, input cost B, a rate distortion R and D is achievable if and only if R is less than this mutual information and D is larger than the expectation of this function D, which we'll define in a moment, for some input distribution that satisfies the input cost. The function D is basically the expected conditional loss given the transmitted symbol X, where this conditional loss is basically obtained with the optimal, let's say, one-shot estimator, say a single letter estimator that estimates the state given the input and the sensing output. And this can actually be found in terms of the posterior distribution of the state given input and sensing output. So one can calculate this posterior distribution. This, of course, will depend on the input distribution Px, and then basically point-wise for every X and Z find the best S star. And this is basically has a little bit the meaning of let's say so-called posterior mean estimator if the metric here was a quadratic error, but in general it's somehow generalized this posterior mean estimator to a fully general case. Good. So well, this is nice. Is a relatively simple result to prove. In particular, what we have here is that we can define a capacity distortion cost function, C of dB, as the supremum of all achievable rates R for given D and B. So basically, as a corollary of this theorem, we have this capacity function is the maximum of the mutual information xy given u, where the maximum is taken over all input distributions that somehow satisfy this constraint on the estimation distortion and satisfy the constraint on the input cost. In addition, the maximization of this mutual information with respect to Px, of course, mutual information is concave with respect to the input distribution. These constraints are linear with respect to the input distribution, so they are convex constraints. So the whole maximization here is a convex optimization problem. Of course, it may not be easy because it's we are maximizing over a space of distributions. But for example, for easy cases that are either discrete or that can be easily discretized, one can resort to a modification of the Blehart-Arimoto algorithm and calculate this capacity. In particular, this function is non-decreasing and concave in the distortion and in the cost. Generally, there is a minimum cost for which basically the set of admissible distribution is non-empty. And we can define also a minimum distortion, and the minimum distortion is, in fact, when we care only about the sensing part. So basically, if we choose the Px to minimize the expected distortion, well, this will be a minimum possible distortion, and we can also pinpoint the corresponding rate as the mutual information corresponding to the input that achieves this minimum distortion. Of course, if this minimum is unique, then there is only one given distribution, which is, say, estimation optimal. If this minimum is non-unique, then basically one can still optimize over all the distributions that achieve this minimum. On the other hand, the capacity distortion cost function increases with D for any given B, and it saturates. It saturates where? It saturates to the capacity of the communication only problem, where we completely disregard the distortion. And in this case, this will stay at that level for all the D larger than this D max, where the D max is the average distortion achieved for the input that achieves this communication capacity. Of course, again, if this input is not unique, then one can further optimize. So let's look at an example which is very instructive, because essentially the sort of trade-off between rate and distortion and cost has always the same shape. So this is a super simple case where we have a memoryless channel with a real value. The input is X, the state is multiplicative, and then there is additive Gaussian noise. And then we have a observation channel, which is simply a physically degraded version of the communication output, so by adding more noise. And for example, we know everything about this, right? Because we know that the capacity, when we disregard completely estimation, is obtained by Gaussian inputs, and we can calculate it exactly. The minimum the corresponding distortion can also be calculated by this expectation, and the minimum distortion is achieved for basically X with a constant envelope, but X with a constant envelope can still communicate messages by binary antipodal signal, and therefore we can calculate these the minimum rate actually the best rate corresponding to the minimum distortion, and so we can pinpoint the corner points, and all the points in intermediate can be actually found here by discretization and using the Black-Hat remoto, and so we see something like this. Basically, the interesting thing is that, so the corner point I was talking about are this extremum and this extremum. Here is the saturation, where for distortions larger than this number, basically the capacity is the unconstrained capacity of the underlying channel. And of course, one can, for example, design achievability schemes that do time sharing between these corners, or more, if one works a little bit harder, find the distribution that achieve this optimal boundary. The naive scheme that would basically alternate from say a pure sensing situation that communicate no information and a pure communication case where completely disregard sensing, and therefore basically in this case the sensing error would be like the using this only the prior distribution of the state, but which is in this case is meaningless. You just get the variance of the state. Would be of course much worse than doing time sharing between these corner points. Now, what is interesting here is that even for a system that is completely designed for communication only, so it's designed to achieve this capacity, there is a huge gain, a potential huge sensing gain, by endowing the system with a sensor. If we are interested in estimating the state, it means that somehow this result suggests that we can use communication waveforms that are designed for communication as also for sensing. And this actually is true. It has been noticed in many communication theoretic papers that if you take an OFDM signal, or OTFS signal, as long as you know the data that are transmitted, so we are in the monostatic case, right? These waveforms have a span enough time and bandwidth, and if we use MIMO enough, you can steer in space to obtain all sorts of parameter estimations without using the traditional, let's say, radar waveforms. What is the catch here? Well, the catch is complexity, because of course, if you have like a chirp designed for radar, the processing to extract the estimation is much easier than if you have a wideband data modulated signal. For example, it's very easy to design full duplex radars that are based on chirps, because the transmit and the receive signal are never at the same frequency. But if you use the whole bandwidth with, say, OFDM, the full duplex is more complicated. Then there is another interesting fact, is that there is a potential for coded, I call it coded pilot gain. So imagine that we have a system that is only designed for sensing and does not communicate any information. Actually, we can achieve the same distortion and still be able to communicate a pretty sizable fraction of the overall capacity. And this is simply, instead of sending the same deterministic waveform all the time, we can use a library of pilots or library of probing signals and basically communicate information through which probing signal we use, right? So that's also an interesting thing. And this is like a sort of recurrent theme in all this literature, is that we can approach the problem more in these directions, and the direction of communication waveforms, and do some estimation on top of that, or some sort of coded radar signals, and so use this direction. Okay. So what happens when we consider stricter notion of achievability? When we consider achievability with the same definition as before, but now our criteria are the maximal error probability, so the maximum over the messages of the error probability, the maximal distortion, where we take the conditional average distortion and we maximize over the messages, and the stricter code word, say per code word admissibility condition. But the good news is that the results in theorem 1 under these memorize nice conditions holds verbatim. So the capacity region or the depth region described by theorem 1 does not change. What changes is the proof. So proving these results is more involved. In fact, one probably the best way to prove these results under this condition is to use, for the achievability, is to use Feinstein's lemma and combine with some weak low large numbers. Other approaches may use so-called robust joint typicality, but they follow in a more cumbersome way. So that's good news. It means that as we already know also for the capacity without sensing, basically in these conditions, the capacity under worst case error probability or average error probability is the same. In fact, you can prove the converse under the more relaxed conditions, and then all what you have to do is to prove the achievability. Great. So now I want to talk about log loss. This is in fact work mainly due to Hamdi Jude that has a very nice interpretation because naturally introduces this sensing mutual information as like a quantity within a clear operational meaning. So what is log loss? Log loss is when the sensor uses, in fact, wants to produce like a soft estimate of the state. So we are not interested in an estimate, but generating a probability distribution on the state. So the output of the sensing function is a probability distribution, and then we can define this loss function, which is essentially minus the logarithm of the posterior probability of a given state sequence, given, of course, the code word, the message which is known, and the sensor output. So theorem 2 is basically the particularization of theorem 1 to this loss function, and it says that for every B, the R and D pair is achievable even if and only if R is less than the usual mutual information and D is larger than this conditional entropy. And for some input distribution and for admissible input distribution. So basically, the result follows from this lemma that says that for any say sensing function that generates a distribution on the state as output, the log loss is greater or equal than this conditional entropy, and this conditional entropy in fact is obtained when we choose as the distribution the true posterior distribution of the state sequence given the observation and the code word. So how this sensing mutual information gets into the picture? in this setting, the entropy of the state is fixed because the distribution of S is given, is part of the problem. And S and X are independent. So this means that the mutual information between S and Z given X can be written as the difference between the the entropy of S minus the conditional entropy of S given Z and X. And therefore, the region in theorem 2 can also be described in this way. So when we define the sensing rate as this difference, basically. So we have this upper bound on the rate and upper bound on the sensing rate in terms of the mutual information between the state and the output given the input. It's interesting to see. So, for example, when the U is equal to S, so when the channel state information at the receiver is perfect, we see this sort of exchange role. So this mutual information is between input and communication output given the state, and the sensing mutual information, the role of X and S are exchanged. So this is the mutual information between the state and the output given the input, which is kind of cute and is maybe interesting just to look at this mutual information as a quantity with an operational meaning. One more thing is that the Pareto boundary, again, can be characterized by solving this problem for all possible non-negative weights lambda. This will sweep, the boundary of this region. And of course, the first mutual information is concave in Px. The second mutual information is linear in Px because X is in the conditioning. So the whole thing is, again, a convex problem. And so, again, we have that, as before, because this follows from what I already said before, is in principle, solving this problem should be doable. Of course, optimizing our space of distribution may be still very difficult. And so for, say, high-dimensional problems or problems with a continuous alphabet, where discretization is infeasible, basically solving actually this problem, having like a good numerical ways to solve this Pareto boundary is still a pretty hard problem. Anyway, one more thing about this sensing mutual information is that there is even a little bit of an extended meaning that goes beyond log loss. And this comes from this theorem that basically applies to any estimator of the state, not only so any estimator and any loss function, not only log loss. Here I added this condition that the estimator can be decomposed per letter. Is probably not needed, but just to be sure. So basically it's additive, like for example, Hamming distance or square error. And basically the theorem says the following: for any estimator of the state that say function of the message and the sensing output, the average distortion obtained by this estimator is lower bounded by the inverse of the rate distortion function of the state calculated in the sensing mutual information. So this is like a bound that somehow can be used as people like to use Kramer-Rao bounds and things like this. Of course, Kramer-Rao bounds are tight under certain condition. There is no general tightness result for this apart from the log loss case. Of course, if L is log loss, then we fall back to the whatever I said before. But this, I think, gives an interesting, let's say, operational meaning to the sensing mutual information, because the general idea is that if the sensing mutual information is large, well, this bound becomes small, and somehow we hope that this means that the sensing is good. This object is kind of interesting because it separates the role of the state distribution from the sensing mutual information. Basically, the rate distortion function of the state depends only on the loss function, and of course the representation alphabet, say S hat is this output space of the sensor, but it is a minimization of this mutual information with respect to the joint distribution of S and S hat, and is completely disconnected from the actual estimator and estimation problem. This is only a problem of how well we represent the state with respect to this loss function. And in contrast, this sensing mutual information has nothing to do with this particular sensor. It's something that lives on its own. In fact, we see is the relevant quantity under log loss. So we have this sort of separation of roles, which I think makes the sensing mutual information a useful quantity in general. So in other words, what I'm trying to say is that looking at achieving points on the Pareto boundaries between these two quantities may be a good idea. Okay, so let's get into a more concrete case, which is the MIMO Gaussian case, which is, of course, related to wireless communication. So the idea is that we have, for example, a base station that multiple antennas that is transmitting to somebody, and at the same time is somehow illuminating some targets. And we have sensors that collectively, of course, all together, they form like a multi-antenna sensor, wants to estimate some parameters from the targets. So the channel model is like this, where we have now basically this H is our state for communication, G is the state for sensing. Generally speaking, G is a function of a set of parameters, eta. And again, we have the communication problem and the sensing problem with a monostatic, so the sensor knows the transmitted message and wants to come up with an estimate of the parameters. We may have or not have channel state information at the transmitter. Most results have considered this channel state information at the transmitter present and perfect. So to make the problem will be tractable anyway, to write expressions in terms of mutual information, but to go beyond that and have even more explicit expressions, then we need to do some simplifications. For example, the case of perfect channel state information at the receiver and perfect channel state information or no channel state information at the transmitter. Okay, so this is basically, okay, we can map this problem into the previous language. It is completely let's say, consistent. In the case where, so in order to preserve the memoryless nature of this model, we assume that the channel is so-called block fading. So there is a coherence block of length t, and in every coherence block, the state is constant. So the H and G and eta are constant, and then they change in an IID fashion across the blocks. and somehow the block length or the coherence block length of the communication channel and the sensing channels is the same. And in addition, coding takes place over an arbitrarily long sequence of those blocks. So in other words, the input alphabet and output alphabets are matrices. That's the classical space-time communication, where the input is an antenna times time matrix, and or it could be time frequency, right? As long as we have this, this block fading assumption. The channel is memoryless because there is no memory across the blocks, and therefore all the machinery that we have seen before applies here verbatim. In terms of input cost, something that makes sense from a physical viewpoint is, of course, transmit power. And by far the most studied input cost is the so-called short-term power constraint, which means that basically for any channel realization, even when the transmitter knows the channel and therefore it can shape the input signal depending on the channel knowledge, still the trace of the conditionally expected covariance of the transmit signal is less than some total transmit power. This means that this constraint is satisfied per coherence block, or per code, not per code, or per letter. A letter is a whole matrix here. So that's why it's called the short-term power constraint. There is another version of these constraints where we remove this conditioning, and so we only impose that this is true on average. Is normally referred to as a long-term power constraint, and from an operational viewpoint, this means that we can do some sort of water filling in time. So sometimes in some blocks we use more power, in some other blocks we use less power, as long as over a long sequence of coherence blocks the power constraint is preserved. This, of course, could also be studied, but most results, existing results, have referred to this constraint. In the age of massive MIMO, so let's say when you have a lot of antennas, there is not a big difference between these two constraints. If you have only, low-dimensional spatial channels, there is difference. There is quite a bit of difference. But anyway, so let's talk about estimation. So we look at the estimation of parameters, and these parameters, as I say, is in fact a parameter sequence that changes from block to block because we want to preserve the memoryless machinery here. And what we have here is that something that people have looked at is Cramer-Rao bounds. Cramer-Rao bounds refers to mean square error. There are lower bounds to mean square estimation error. And we have to put a little bit of order. The picture is a bit messy, at least for me. Maybe for somebody everything is perfectly clear, but I think it's a little bit of a jungle. Basically, the classical Cramer-Rao bound is for the case of non-random parameters, where we have an observation model where Z is the observation, is distributed according to a conditional distribution, and eta is non-random. And one can define basically this expectation with respect to the measure of observation given the parameters, and it turns out that for any unbiased estimator eta hat, the mean square error is less or equal than this quantity. This is known as Cramer-Rao bound, and it depends on this matrix, which is the Fisher information matrix, that involves only the conditional distribution of the observation given the parameter. There is no averaging with respect to the parameter because the parameter is non-random. Now, in the setting we have here, we have two problems. For problem number one, the parameter is random, is a random variable. Problem number two, the observation depends also on the input, and the input is known to the sensors. So, in other words, we don't have this, we could get this sort of average out, but the sensor knows the input. So we have one extra conditioning here with respect to X. So in estimation theory, typically when you have this extra conditioning with respect to something else, these are called nuisance parameters because they act here in the conditioning, but it's not really what we want to estimate. And then we have several different variants of this Kramer-Rao bound. So one can define, for example, the conditional Fisher information matrix, where we condition also with respect to the input, and which has exactly the same form as before. We simply expand the parameters to the wanted and the nuisance. And then there is something called the Bayesian Fisher information matrix, which is obtained by basically averaging when we basically consider the joint distribution of z and eta given x. So this splits into a prior distribution of eta that gives rise to this term, and another term which is the conditional expectation of this conditional Fisher information matrix with respect to eta given x. And at the end we have a sort of basically we have to still remove the presence of x, and this is done through one layer of expectation on top, and this is called the so-called Miller-Chang version of the Kramer-Rao bound, and this will be a Miller-Chang version of the Bayesian Kramer-Rao bound. So at the end, this is the trace of the expectation of these conditional Bayesian Fisher information, where the conditioning is with respect to the input. Then there is another version that I call expected modified Kramer-Rao bound, where the expectation is done in a different way. So we can define first a so-called modified Fisher information, where we do the expectation of the conditional Fisher information with respect to the nuisance parameter first, and condition with respect to the wanted parameter. And then it turns out that one can prove that the trace of the expectation of the inverse of this modified Fisher information is also a lower bound. So it's a little bit confusing, and it turns out that in certain papers, people have focused on the Miller-Chang version of the Bayesian Kramer-Rao bound. In another work, people have looked at this expected modified Kramer-Rao bound. Or one can also consider directly the minimum mean square error estimation, and for the case where G is correlated Gaussian, and in fact we don't want to estimate some eta, but we want to estimate directly G, and then one can work out errors, say, is like saying first estimate G and then extract from the estimate of G whatever estimate of the parameter, but we only look at the estimation of G. Then one can directly handle the minimum mean square error. And so there is no need to look at Kramer-Rao bounds. Okay, I'm running very late, so I would like to say here just a summary of these results. Basically, in the paper that got the best joint paper award of the ComSoc and Information Theory Societies this year, which is I was just random quote, or all the credit goes to the other people. But basically, this rate Bayesian Kramer-Rao bound was studied quite in depth. And the main message of this paper is that basically the function, the way the input somehow influence the sensing metric, which is this Kramer-Rao bound, is through its the sample covariance matrix of the input matrix. And it turns out that one, by studying this function, one can conclude that the trace of the sample covariance matrix must be deterministic, and in particular, the sample covariance matrix must be in the solution space of this problem, which is a convex optimization problem. When the solution is unique, basically it means that the sample covariance matrix of the input must be deterministic to be, say, estimation optimal. And this hints on, first of all, in a sort of semi-unitary plus beamforming type of signaling, where basically our input letters are semi-unitary matrices with a sort of mask that somehow puts in shape the spatial coordinates and put the power in the right direction for estimation. And one can also find, using results from packing in the Stephen manifold, one can find the ISNR rate achieved for this, say, sensing optimal input. On the other hand, the other corner point where we are communication optimal, then we know that the capacity is obtained by Gaussian inputs, where the input covariance is obtained from the channel matrix by water filling. And therefore, this is the well-known ergodic capacity with the perfect Ceresel information and short-term power constraint. What is interesting is also to quantify the loss incurred in the loss in sensing performance incurred in using these communication optimal distributions, and this was done in the paper. There is a notion of sensing degrees of freedom and loss of sensing degrees of freedom, and yeah, so this is basically the main thing. So the similar results have been obtained more recently by another co-author, looking directly at the case where the parameter we want to estimate is the sensing channel matrix, which is also Gaussian, and then we can directly analyze the actual mean square error. One can find a number of interesting results, but in particular, again, the fact that the sensing optimal signaling has a deterministic covariance, and so we fall again into this semi-unitary plus beamforming, I call it, type of signaling. In addition, yeah, so one can also, replace using Gaussian inputs and find outer bounds. So since I'm running out of time, what I want to say is that these papers have somehow illustrated the fact that there are some fundamental trade-offs in sensing and communication. That one is about subspaces. So this is this sort of beamforming aspect, is how we shape the covariance matrix to somehow illuminate the target, but also send signal energy in the direction of the receiver. And the other one is this deterministic random trade-off, is that the optimal signaling for communication is somehow conditionally Gaussian, given the channel, and the optimal signaling for sensing has this flavor of deterministic sample covariance, and therefore it hints into some sort of unitary or semi-unitary signaling. So one interesting, very recent result is to look at the large T regime. So the large T regime, or when the coding block length is span one coherence block, so there is no averaging. So we are going a little bit away from this memoryless case. What happens is that in this case, and the theory is a little bit is actually very interesting, but it requires time. So I don't know how much time I still have. But basically, what happens is that in a recent work, Hamdi and co-authors have shown that basically using this other version of the Kramer-Rao bound that I said is some modified Kramer-Rao bound, one can basically show that the so-called random trade-off, random deterministic trade-off disappears. In other words, they can prove a rigorous theorem that in this case of large coherent block, where the coding spans a single coherent block, and so basically there is the channels and the parameters are constant, can be considered as arbitrary constants. There is no averaging with respect to those quantities, and it turns out that the region of admissible of achievable R&D can be exactly characterized. And basically is achieved by, let's say, at least this expression is the expression of the Gaussian capacity, and this is exactly this single letter expected modified Kramer-Rao bound that I was talking around before, which in this case for this type of channel turns out to be only a function of the covariance matrix of the input, not the sample covariance matrix, but the actual the statistical covariance matrix. So basically, it turns out that somehow we can use Gaussian input are optimal. The proof is actually a bit complicated. It requires a lot of details, and a lot of people have somehow. So again, it requires Feinstein's lemma. It requires some results on the asymptotic tightness of this expected Kramer-Rao bound with respect to the minimum mean square error estimation. But it's kind of interesting. So I want to say two quick more things. So one is the problem of sensing with feedback. So sensing with feedback is when simply the sensor now is somehow in contact with the transmitter. So basically, the sensing channel can be seen as a sort of implicit feedback for that can help communication. Now, it turns out that when we have the memoryless case, good news, we can define the problem in the usual way, where now the code with feedback is defined as a sequence of functions that map the causal feedback sequence and the message into the inputs, etc., etc. The good news is that for the memoryless case, the rate-distortion-cost achievable region is exactly the same as theorem 1. So in other words, whether this thing, the sensor, tries to help the transmitter or not, the region doesn't change. And the reason is that the well-known result that for the memoryless case, feedback does not increase capacity. Things are very different when the state has memory, because when the state has memory, then feedback increases capacity generally. And even without the state estimation problem, the general problem of the capacity of channel with feedback and memory is an open problem. So there are partial results, for example, assuming the so-called in-block memory. In-block memory, the state remains constant for finite blocks of symbols, and then it changes IID across the blocks, and coding is done over a long sequence of blocks. A typical case, for example, is what I call the beam pointing channel, where the state, for example, is the angle of departure of a target, and we want to, at the same time, estimate the target position and communicate with the target. So this, for example, is a sensing-aided beam pointing or sensing-aided beam tracking, call it as you like. And of course, the state changes slowly with respect to the communication, so this in-block memory becomes relevant. And so, for example, we have studied this case in a super simple case where the state is a binary vector, is a one-hot encoding that tells you in a set of discrete angle that could be like a beam-forming code book where the target is, in which beam the target is. And we consider just a deterministic binary channel. And still, the problem is absolutely not trivial. It boils down to some very complicated dynamic programming. So this is to say that even as soon as you introduce memory in these problems and feedback, things can become really, really complicated. So I will jump. So just maybe a word. So basically what happened is that the strategy here is that the transmitter is trying to locate the target, and at the same time also somehow maximize the entropy of the output. So it's not only trying to locate the target, but it's also trying to communicate. And one has to design these strategies and find achievable. And in this case, also we have conversely. So in this case, for the binary case, the problem is essentially solved, but in general, it's very difficult. One fact that one can see that even for this simple case, if we compare the joint strategy with strategies that do separate, so they do like it's done in system today, that you first do beam sweeping and find where in which beams the target is and then communicate. Well, those strategies can be extremely suboptimal. So we are at the end. I want to say one word on the bistatic model. Or the bistatic model, as I say, is when the sensor does not know the message. It knows the code book, but does not know the message. So this problem has been studied recently by Caire, Wang, and co-authors, and it gives a set of interesting results. So let me just summarize. First of all, achievability strategies. Achievability can be done, for example, by blind estimation. So we just care about communication, and the estimator takes the presence of this unknown input as nuisance. So it just looked at the distribution of the posterior distribution of the state given z without the conditioning of on the input. And so we have this leads to a lower bound in general on the best possible capacity distortion. Achievability strategy 2 is a partial decoding. So basically we can use superposition coding and enable partial decoding at the sensor. So basically we optimize with respect to auxiliary random variable that is a little bit like the center cloud, such that the sensor can somehow decode the center clouds, and so somehow use this to help estimation. So the estimator now use also the variable u, not just the variable z. And by doing this, basically, there is like a subset of the message that must be decoded also by the sensor, and this somehow imposes a so-called degraded message set for which superposition coding is optimal. But of course, this is not optimal in this context. This is an achievability strategy because we do it by design. And then, of course, there is the full decoding strategy where we require the sensor to decode the code word. In this case, the code word becomes known, so the estimator can use the input X also, but of course we get a hit in the rate because the rate will be the minimum between these two mutual information, which is in general less than just this one. So interestingly, one can also prove upper bounds and using a technique quite similar to the converse of the broadcast channel with the degraded message set. So it's based on finite inequality and Caesar sum identity. One can prove an upper bound like this. And it turns out that when the sensor is a degraded version of the receiver, of the communication receiver, then this upper bound coincides with the partial decoding. So this is the case where we have an exact characterization of the capacity. Of course, this degradation here is like physical, but the same results holds for the more practical, say, stochastic degradation. So in other words, when the sensor is more noisy, in some sense, this would go through. Okay. So I'd like to conclude with, I again apologize for not referencing by name all the authors of all the results I've been talking about, but they are all here, hopefully. I would like to point out also some inspiring and useful tutorials that appeared recently. This one by Meraza, Michel, and Shlomo. And of course, this very nice paper appeared on BITS, the Information Theory magazine, that talks about these aspects. And with this, I'd like to conclude this talk. A little bit over time, I apologize.
Thank you, Giuseppe, for a very wonderful, very informative talk. So now is the Q&A session. We do have received a number of questions, so I will pick 3 to 4 of them to ask you. So the first question is about the performance metrics for sensing communication. So from the perspective of the information theory, how to unify the performance metrics of both sensing and communication. So if we can unify them, it may be potentially beneficial for us to do some resource allocation and system design. So can you give some comment on this question?
Yeah, so I think that the basic problem that I stated at the beginning is with respect to sensing loss function that is somehow arbitrary. It depends on the application. As you can see, this sensing loss function plays the role of some constraint on the input, at least for the memoryless case. So in other words, it's kind of similar to the input cost function, right? Why we use input power? Because it makes sense from a practical viewpoint, but in general, for a discrete memoryless channel, you can any non-negative bounded mapping between the input alphabet and the reals would be a valid input cost, right? So I would say that the general formulation applies pretty much to anything you can think of. My personal taste is that because of the significance of soft estimation, the log loss is a nice way to look at as one unified problem formulation. That auxiliary result that I talked about, that somehow sensing mutual information combined with the rate distortion function of the state you want to sense, provided, of course, that this can be calculated, gives this sort of rate distortion lower bound, somehow decouple the two aspects. I would say if one wants to design a system without knowing exactly what is the performance, the sensing performance that you want to optimize, I think that looking at the sensing mutual information or equivalently using log loss seem to be a very good strategy. So I would say in a sort of agnostic design, imagine you are a company or an operator and you want to offer sensing as a service. So you want to have like an API for verticals such that people can tap into this API and extract sensing information from a wireless network and do something. But we don't know what they want to do, right? It depends on the application. Somebody wants to count cars, somebody wants to provide safety to vulnerable roadside users, somebody wants to do intrusion detection, who knows, right? Somebody wants to run a digital twin of a city. It's difficult to, so how do we design a system, right? So I think that this log loss and sensing mutual information makes a lot of sense to design a system that is say good for in many ways. Of course, if one has a more specific application in mind, say for example, for this feedback case where the sensing helps the transmitter to locate the target because eventually basically we want to do beam tracking, like or radar aided beam tracking. That's a different problem. There you have a very specific application in mind, and then you can do it for your specific application.
Thanks, Giuseppe. It's a very, very nice perspective. Actually, I think this is the first time I heard that mutual information can be used as a metric for agnostic designs. Yeah. Yeah. So then the second question is exactly about mutual information. So there are many works on optimizing mutual information between the radar channels and the received echo channel signals. But the question is that the operational meaning of the sensing mutual information is not quite clear. So how it links to other typical sensing metrics such as CRB and the detection probability and MSE. Yeah. So this is the second question.
Yeah, I think this is related to the first. I think that the link to the CRB, honestly, is to be seen. I don't want to say something too stupid here. All what I can say is that the sensing mutual information has a very clear meaning when we talk about log loss. So soft estimation, and has a not so clear meaning, but at least provides this sort of universal lower bound for any performance metric with a nice decomposition, although it may not be tight, but still it tells something. In particular, when we talk about, say, Kramer-Rao bounds, and so, for example, square error, well, there are relationships between mutual information, Fisher information, square error, MMSCI inequality, De Bruyn inequality, the identity. There are these things. There may be something more profound there that relates Fisher information and mutual information, but I'm not fully confident in making a statement here.
Okay, thank you, Giuseppe. So I think there's still lots of work to be done in this to clearly review this. Yeah.
Yes.
And the third question is about I think the input distribution optimization. So how does the optimal input distribution guide the design of practical ISAC system? For example, if one could numerically obtain some trade-off distribution using the Blahoder-Evermoto algorithm, how to use that distribution to design a practical channel coding strategy?
Well, so I think that there is one easy and one difficult part of this. The easy part is for channels that have, let's say, they're more directly related to wireless communications. There is certainly the beamforming aspect, so the shaping of the covariance, or like you call it the subspace, right? That has a very immediate operational meaning in terms of illuminating targets while communicating. Doing it can be translated also into different form of water filling over frequency. I think that this basically is like, I would call it like precoder optimization, because the shaping of this covariance essentially is like a precoder. Then for the distribution of the symbols, well, this is you know, the usual problem of knowing the input distribution doesn't mean that you know how to design good codes, right? We knew that the capacity of the Gaussian channel is achieved by a Gaussian symbols and a Gaussian input distribution since you know, the 50s, but the first capacity achieving codes for even just for the simple additive noise Gaussian channel have been found, you know, like 10 years ago. So the code design is a very different beast with respect to optimizing input distributions. I think that there is a lot of let's say know-how and rule of thumbs. Now we know, for example, that if something can a certain say capacity is achieved by, say, Gaussian inputs with some form of precoding and covariance shaping, well, we know that if you plug in a good code for the Gaussian channel, say a nice LDPC concatenated with I don't know, probabilistic shaping, or some BICMID, something that goes very close, and go through the same precoders, most of the time it works. But of course, this is a rule of thumb, right? When we want to use more exotic signaling, like for example, you know, people have come up with this unitary constellations for space-time coding for different reasons, but they would be useful here, right? You can use this alphabet of unitary matrices as symbols and construct codes on that. Things are a little bit more difficult, and I think that one major problem here is complexity, because these unitary constellations haven't, you know, even at the time of space-time codes, where people have tried, but it's very hard to make these things actually doable in terms of complexity. So I'm a little bit skeptical that dramatically different, say, type of signaling would give like enormous gains. Maybe a slightly different problem is when we use, for example, coded. I call them coded pilots, right? So when we are in that region of minimum distortion and still try to get some rate, right? So the corner point, or the left corner point of the trade-off curve. There, in a different scenarios, for example, in the case of random access, which is a different problem because it's a multi-access problem that I've not talked about here. Everything was like single user, but so people have designed schemes for unsourced random access, and more recently, schemes for unsourced random access have also been used to do some sort of sensing estimation. For example, imagine you have like users that send say these preambles at random, and still the receiver wants to detect the presence of certain preambles. A priori, you don't know which preamble has been transmitted, but also extract, for example, channel state information or presence of obstacles and targets. Identify, for example, if something is a target, or things of this kind. And so there you can see that using, for example, frames with so families of code words with low coherence, and exploiting some sort of compressed sensing style detection yields very good results. So I would say there is a space for this type of designs. There is also the possibility of using learning techniques. You just put as a cost function. You take this, right, with or anything else. Here you can put your favorite sensing distortion measure, and then use a variational representation of these quantities, and use say deep learning to learn a code book that somehow strikes a trade-off between sensing and communication. And there are works that in this respect. So it's definitely something to look at.
Okay. Thank you, Giuseppe, for your very informative answer. So maybe the final question from the audience. So this question is about the bound. So the CRB or BCRB is in general very loose and is only asymptotically achievable under high SNR. So can we use other tighter bounds for sensing in the ISAC information theory work? Does the same trade-off principle still hold for such bounds?
Right. So first of all, it's okay. So all these CRB, they are for the first of all, they are limited to the quadratic error, so the mean square error. Interestingly, what I call, maybe not in an orthodox way, some people may disagree with this name, but I call it expected modified Kramer-Rao bound, which is that particular version of bound, turns out to be instrumental in proving this result. So for large block, where you have, imagine that the state stays constant for the whole block, and the block is thousands of symbols. This result is exact and does not depend on SNR. So the tightness of this bound, so this is the mean square error, or the minimum, or the posterior mean estimator. So this is a minimum mean square error, and this is the bound for any specific input sequence. The tightness of this result does not depend on SNR, depends on N. So in other words, you have always two things in the Kramer-Rao bound. You have SNR for finite N, and you have this waterfall behavior. There is a region where the Kramer-Rao bound is not tight at all, and then you have this waterfall, and then more or less any decent estimator falls on the Kramer-Rao bound. Maximum likelihood, for example, it has this typical behavior of maximum a posteriori in the Bayesian case. But then you have the other side of the medal, which is the large sample, this large sample regime. And in that regime, all these Kramer-Rao bounds are tight. in the sense that we know that when you have a large number of samples and the parameter is the same and you have independent samples, well, first of all, your mean square error decreases like 1/n, and and there is a plethora of Kramer-Rao style bounds that becomes asymptotically tight. And so I would say that in the large coherence time regime is definitely the way to go. The expressions are tractable and elegant. For the final sample regime and the intermediate SNR, so then it's definitely a big problem. On the other hand, one can also argue that in the whole story, if you look at the estimation theory, without, say, disregarding communication, we always try to design estimators that work on the right of the waterfall. So when the Kramer-Rao bound is close to the actual performance of the best known estimators, working on the left of the waterfall is a suicide, right? So in a certain sense is a little bit like I would say a self-fulfilling prophecy that the interesting region for estimation is to work on after the waterfall when the performance of your best shot estimator is good. Otherwise, whatever you do, you're dead.
Okay, thank you for the very nice explanation. Okay, I think that's all from the audience, and that's pretty much for today's webinar. And I would like to thank Professor Giuseppe Caire again for the very wonderful talk and a very insightful discussion on the questions. So we hope to have you again in our future events. Thank you, Giuseppe.
Okay, thank you very much. Thank you.
Okay, so so before we end, please stay tuned for the next session. So the next lecture is entitled "The CRB Rate Trade-off in ISAC: Theoretical Framework, Insights, and Limitations," which will be delivered by Professor Yifeng Xiong at 7 p.m. next Monday, so September 29th. Okay, so that's all for today's lecture. See you.